Hello my friends, and welcome back to Sky Creative Channel. From the roaring blast furnaces of Mexico to precision robotics in modern factories, join us as we explore 5 incredible manufacturing processes that showcase the evolution of industrial craftsmanship. Let's see how today's giants make steel, pipes, and electric motors. We're taking you deep into the heart of Mexican industrial might with Altos Hornos de Mexico, or AHMSA as it's known in the steel world. Now, if you're like me and remember when American steel mills were the backbone of our industrial heartland, you'll appreciate what we're about to show you. AHMSA has been forging Mexico's industrial future since 1942, and their Monclova facility stands as one of the largest integrated steel complexes in North America. Let's walk through their remarkable steelmaking process. Step by step, it all begins in the blast furnace, the towering cathedral of industry where iron ore, coke, and limestone come together in a dance as old as the Industrial Revolution itself. The blast furnace operates at temperatures exceeding 3,000 degrees Fahrenheit, hot enough to turn iron ore into molten pig iron. The principle here hasn't changed much since Abraham Darby perfected it back in 1709, though the scale and precision certainly have. AHMSA's blast furnaces use sophisticated computer controls to monitor oxygen levels, temperature zones, and material flow, ensuring consistent quality that our grandfather's generation could only dream of. Once we have that molten pig iron, it moves to the basic oxygen furnace, or BOF as the industry calls it. Here's where the magic really happens. The BOF process, developed in Austria after World War II, revolutionized steelmaking by dramatically reducing production time from hours to just 20 minutes per heat. Pure oxygen is blown through the molten iron at supersonic speeds, burning away excess carbon and impurities. It's controlled violence on an industrial scale. The Langsat system, positioned precisely above the molten bath, delivers oxygen at pressures that would make your car tires look like birthday balloons. AHMSA's operators monitor this process through sophisticated sensors that measure temperature, carbon content, and slag chemistry in real time, adjusting the oxygen flow and flux additions to hit exact specifications. Now, here's something that would fascinate any old-time foundryman: the continuous casting process. Back in the day, steel was poured into individual molds and allowed to solidify slowly. AHMSA uses continuous casters that pour molten steel into water-cooled copper molds, moving in a synchronized dance. As the steel enters the mold at nearly 900 degrees, it forms a solid shell while the interior remains molten. The strand is gradually bent from vertical to horizontal as it solidifies, guided by precision rollers and electromagnetic stirring systems that eliminate defects. The result? Perfect steel slabs, blooms, or billets emerging in an endless stream, cut to length by robotic torches. This technology, perfected in the 1960s, increased productivity 5-fold compared to traditional ingot casting. NTHE journey doesn't end there. Those semi-finished products head to the rolling mills, where centuries-old principles meet cutting-edge automation. AHMSA operates both hot strip mills and plate mills, each a marvel of coordinated mechanical engineering. In the hot strip mill, massive hydraulic systems generate forces exceeding 10,000 tons to squeeze steel slabs through successive stands of rollers, each one reducing thickness and extending length. The steel travels at speeds up to 60 miles per hour by the final stand, all while maintaining tolerances measured in thousandths of an inch. Computer-controlled cooling systems along the runout table then determine the final properties of the steel, using precisely timed water sprays to achieve desired hardness and strength characteristics. What sets AHMSA apart is their commitment to quality control throughout every stage. Automated sampling systems pull specimens for chemical analysis, while ultrasonic testing equipment scans for internal defects invisible to the human eye. It's this marriage of traditional steelmaking knowledge with modern automation that keeps them competitive in today's global market, producing everything from construction steel to specialized alloys for the automotive industry. Now let's jet across the Pacific to Johor Bahru, Malaysia, where KMU Fabricator operates one of Southeast Asia's most sophisticated steel fabrication facilities. Located in the Tanjung Langsat industrial estate, this company represents the modern face of structural steel fabrication, combining traditional craftsmanship with computer-controlled precision that would make any old-school fabricator both proud and amazed. NTHE process begins with their CNC automatic beam drilling machine. And folks, this is where we see how far we've come from the days of hand marking and manual drilling. This machine uses 3-axis simultaneous drilling capability, meaning it can drill holes in multiple planes at once while the beam moves through the system. Laser measuring systems scan the beam profile, compensating automatically for any variations in the raw material. The drill heads, equipped with carbide-tipped bits, can handle holes from 1/4 inch to several inches in diameter, adjusting speed and feed rates based on material thickness. The entire operation is controlled by CAD's CAM software that reads engineering drawings directly, eliminating human error and ensuring that hole patterns match specifications to within a few thousandths of an inch. Next comes their CNC automatic cutting machine, employing either plasma or oxy-fuel technology depending on material thickness and required edge quality. The plasma cutting system ionizes compressed air or nitrogen into a superheated jet reaching 45,000 degrees Fahrenheit, hot enough to slice through steel like butter while maintaining cut edges clean enough for welding without additional preparation. The gantry system moves the cutting torch along programmed paths with acceleration and deceleration controlled to minimize vibration, while height sensors maintain optimal distance from the material surface. Their CNC automatic punching machine is a symphony of hydraulic power and computer precision. Using force up to 200 tons, it can punch holes, slots, and notches in steel plate up to 1 inch thick. The turret carries multiple tool sets, automatically selecting and positioning the right punch and die combination for each operation. What's remarkable here is the speed. Modern CNC punching machines can execute up to 600 hits per minute, with positioning accuracy better than 5/1000ths of an inch. The machine's computer optimizes the punching sequence to minimize material stress and prevent distortion. NFOR prefabricated plates requiring manual attention. Skilled operators use manual punching machines for specialized operations where human judgment still matters. These traditional machines, while requiring more operator skill, offer flexibility for custom work and prototype development. The bandsaw machines they employ use continuous loop blades running at carefully controlled speeds, with carbide-tipped teeth that can slice through solid steel billets. Cooling fluid floods the cut zone, preventing blade overheating and ensuring clean cuts on marked points. NTHE finishing department showcases their attention to detail. Manual shot blasting removes mill scale and surface contaminants using steel grit propelled at high velocity through specialized nozzles. This creates the profile necessary for paint adhesion, essentially creating microscopic anchors in the steel surface. The primer coat, typically a zinc-rich formulation, goes on next, providing sacrificial protection against corrosion. Hole covers protect threaded connections in critical surfaces during subsequent coating operations. NTHE multi-coat painting system builds protection layer by layer. Each coat serves a purpose. The second coat provides additional corrosion resistance and begins building film thickness, while the final coat offers UV protection and a specified appearance. Between coats, inspectors check for holidays, mist spots, and measure film thickness with electronic gauges, ensuring compliance with specifications that might call for total thicknesses of 8 to 12 mils. Supporting operations include their bending machines, which use precision dies and hydraulic pressure to form angles and channels without cracking or distorting the material. Their lathe machines handle cylindrical components, removing material with single-point cutting tools while the workpiece rotates at controlled speeds. The automatic marking machine uses either dot peen or scribe technology to permanently identify parts with heat numbers, piece marks, and assembly information. The shearing machine makes straight cuts using opposing blades, one fixed and one moving, creating clean edges on plate material. It's this comprehensive capability, from CNC automation to skilled manual work, that makes KMU Fabricator a leader in structural steel fabrication for Malaysia's booming construction and petrochemical industries. Friends, let's head to Austria, where Voestalpine Tubulars has perfected the art and science of seamless pipe manufacturing. Now, seamless pipe might not sound exciting until you understand where it's used. Deep oil wells, nuclear power plants, high-pressure hydraulic systems, and critical aerospace applications. These pipes have no welded seam, making them stronger and more reliable than welded alternatives, a distinction that can mean the difference between success and catastrophic failure in demanding applications. NTHE journey begins with carefully selected steel billets, cylindrical blocks of solid steel that have already been through their own rigorous production process. These billets arrive with certified chemistry and mechanical properties, typically made from specialized alloys designed for specific service conditions. Voestalpine's quality control starts here, with ultrasonic testing to detect any internal defects that might compromise the final product. NTHE billets enter a rotary hearth furnace, a circular heating chamber where they're raised to forging temperature, typically between 200 and 400 degrees Fahrenheit. This heating must be uniform throughout the billet's cross-section to prevent cracking during subsequent forming operations. The rotary design ensures even heating as billets slowly progress around the furnace circuit, a process taking roughly 2 hours. Modern furnaces use regenerative burners that capture waste heat, improving efficiency while maintaining precise temperature control through multiple zones. Here's where it gets fascinating: the piercing process. The glowing billet moves to a rotary piercing mill, also called a Mannesmann mill after its German inventors from the 1880s. This machine uses 2 barrel-shaped rolls set at opposing angles, rotating in the same direction. As the billet is forced between these rolls, it's simultaneously rotated and pushed forward onto a piercing mandrel, a bullet-shaped tool positioned on the center line. The combination of compressive forces and rotational motion causes the center of the billet to fail in tension, opening up around the mandrel to create a thick-walled hollow shell. It's metallurgically brilliant, using compression to create tension, forming a hole without removing any material. NTHE rough tube, still glowing orange, proceeds to elongation mills where it's stretched and reduced to closer dimensions. These mills use sets of rolls arranged in stands, each successive stand reducing the wall thickness and increasing the length. Some operations employ a mandrel bar running through the tube's interior, supporting the wall and controlling inside diameter. The precision here is remarkable. Computerized systems adjust roll positions in real time, compensating for temperature changes and material variations. Next comes the stretch-reducing mill, sometimes called a sizing mill, consisting of numerous roll stands arranged in series. The tube passes through perhaps 20 or more stands, each making a small reduction in diameter. This cold or warm forming operation achieves final dimensions while work-hardening the material, improving strength properties. The entire stretch-reducing mill operates as a coordinated unit, with each stand's speed precisely synchronized to prevent tension buildup or compression that could damage the tube. Heat treatment follows, crucial for achieving specified mechanical properties. Pipes may be normalized, heating them above the critical temperature and air cooling to refine grain structure. Others require quenching and tempering, rapid cooling from high temperature, followed by reheating to a lower temperature, producing an optimal balance of strength and toughness. Voestalpine's heat treatment furnaces use atmosphere control to prevent scaling and decarburization, maintaining surface quality throughout. And finally, each pipe undergoes rigorous testing. Ultrasonic inspection detects wall thickness variations and internal flaws. Electromagnetic testing finds surface defects. Hydrostatic testing proves pressure integrity. Dimensional inspection confirms geometry. Only pipes meeting all specifications receive certification for shipment. This comprehensive approach, combining century-old principles with modern automation and quality control, has made Voestalpine Tubulars a trusted name in industries where failure simply isn't an option. Let's talk about one of the most impressive pieces of steelmaking equipment you'll ever see, the Danieli Centromet 3-strand billet caster. Danieli, an Italian company with roots stretching back to 1914, has been at the forefront of continuous casting technology, and their 3-strand system represents the pinnacle of efficiency and reliability in billet production. NTHE process starts in the tundish, an intermediate refractory-lined vessel that receives molten steel from the ladle. The tundish serves multiple critical functions. It allows continuous casting even during ladle changes, provides residence time for inclusion flotation, and distributes steel evenly to all 3 strands. From the tundish, steel flows through 3 separate slide gate systems into the mold assemblies. These slide gates are engineering marvels in themselves, using refractory plates that slide across each other to control flow rate with precision. They respond to level sensors in the molds, adjusting flow automatically to maintain consistent steel height despite variations in casting speed or steel temperature. and THE molds themselves are where the magic begins. Made from high-conductivity copper with chromium plating, these water-cooled molds are where molten steel first solidifies. Cooling water flows through channels at velocities, designed to remove heat rapidly without causing thermal shock. As the steel contacts the cold copper walls, a solid shell forms instantly, perhaps a quarter-inch thick. This shell must be strong enough to contain the still molten core as it's pulled downward. The molds oscillate vertically at 60 to 200 cycles per minute, a motion that prevents the solidifying shell from sticking to the mold walls. Mold powder, added at the top, melts and infiltrates between the shell and mold, lubricating the interface and controlling heat transfer. In A's, the billet emerges from the mold. It enters a sophisticated containment and cooling zone. Multiple stands of rollers support the strand at precisely calculated intervals, preventing bulging from the metallostatic pressure of the liquid core. Each roller pair applies just enough force to support, without deforming the billet. Primary cooling sprays hit the surface immediately below the mold, using finely atomized water to continue solidification. The spray patterns and water flow rates are computer-controlled, varied along the strand length to match the solidification profile. In secondary cooling zones continue the process as the billet descends, guided by the precisely aligned roller system. Modern casters use electromagnetic stirring in these zones, applying rotating magnetic fields that stir the molten core. This stirring refines grain structure, promotes uniform composition, and prevents centerline segregation where impurities might concentrate. Temperature sensors monitor surface temperature continuously, feeding data to the control system that adjusts spray cooling to maintain optimal thermal conditions. THE strand withdrawal system, driven by powerful pinch rolls, pulls the billet through the machine at controlled speeds, typically between 2 and 4 meters per minute. This speed is crucial. It must match the rate of solidification, ensuring the core is fully solid before the billet reaches the cutting area. The withdrawal system also maintains constant tension, preventing soft reduction that could cause internal cracking. At the runout table, the continuous strand is cut into discrete lengths by high-speed shears or traveling torch cutters. These billets, still glowing red at perhaps 1/800 degrees, are marked with identification numbers and directed to cooling beds, or, in some operations, sent directly to rolling mills while still hot, saving the energy that would otherwise be needed for reheating. What makes Danieli's 3-strand design particularly impressive is the efficiency. One tundish feeds 3 independent casting lines, tripling productivity while sharing common support systems. The automation level is extraordinary, with thousands of sensors and computer control loops maintaining stable operation. It's this combination of metallurgical knowledge, mechanical precision, and computer control that produces billets of consistent quality, ready to become everything from reinforcing bars to precision machined components. Finally, let's explore something completely different: the Knight Group's fully automated stator production line with robotic integration. For those who remember when electric motors were hand-wound by skilled craftsmen, this represents a quantum leap in manufacturing technology. End stators are the stationary electromagnetic components in electric motors, consisting of thin laminated steel sheets stacked together and wound with copper wire. The production line begins with automated stator core handling, where robots equipped with vacuum grippers lift and position lamination stacks with repeatability measured in hundredths of a millimeter. These aren't your grandfather's industrial robots. They're equipped with force sensors and vision systems that allow them to adapt to slight variations in material positioning. THE paper insertion system comes next, automatically feeding insulation material into each slot of the stator core. This polyester or Nomex paper prevents the copper windings from contacting the steel laminations, critical for electrical safety and motor longevity. The insertion mechanism uses pneumatic fingers that navigate the slot geometry, sliding paper precisely into position at speeds impossible for human workers to match while maintaining perfect consistency. THE winding process showcases the pinnacle of automation. Modern stator winding machines use needle winding or flying fork technology, guiding copper wire through stator slots in precisely calculated patterns. The wire tension must remain constant. Too tight and it stretches or breaks. Too loose and windings become uneven, affecting motor performance. Several motors control wire feed speed, while tension dancers maintain consistent pull. The winding heads can complete complex coil patterns in seconds, work that would take skilled technicians many minutes. And after winding, automated lacing machines secure the coil ends with specialized cord, preventing movement during operation. Robotic systems then apply varnish impregnation, dipping entire stators in insulating resin before curing in temperature-controlled ovens. This process fills air gaps, improves heat dissipation, and protects against moisture and contaminants. NTHE beauty of NIDE's system lies in integration. Every station communicates with the central control system, tracking each stator through production while adjusting parameters based on real-time measurements. It's manufacturing for the electric vehicle age, where quality, consistency, and speed determine competitive success. From traditional steelmaking to cutting-edge automation, we've witnessed manufacturing's evolution, where human ingenuity continues pushing the boundaries of what's possible.